But then I also want to now start by saying that I have a few questions on the way. So I also want to learn here on the way. So I have a few questions, and the link is now visible there, but I put it also here on the chat so you can answer the question from there or look at the questions. I'll try to remember to mention them when they come up in the slides. But so I'm Tom Bäckström. I'm from Aalto University in Finland, currently leading the kind of new Marie Curie doctoral training network, Privacy for Smart Speech Technology, and also leading a project about trust in speech technology. And yes, so this picture is, of course, complicated, overly complicated, but don't worry, I split it up. It actually plays an important part in this presentation. That's why I wanted to put it here on the front page. But as a background to this presentation, so actually it's continuation from the survey talk I had at Interspeech in 22 in Korea. I did quite a lot of work for that, but then it was proposed to me that I should make a journal article out of it, and I did that. It's currently an archive paper. It now has been in 2 years in review. It's a bit disappointing that it takes so long time to get something accepted. I still don't know what the outcome of that is, but it is archived, this paper, so privacy in speech technology. So I think it can be useful. In this presentation, I have a few updates which are not yet in that paper. I hope to include them in the next round of kind of improvements, or when I get it back to get the review responses back. So I hope to update it again. I just hope that it at some point gets either accepted or rejected, so we can move on, because now it's already 2 years old, and some parts age of it, but some parts, at least the new parts, which are new for the audience, they should not age that quickly, hopefully. So contents, pretty obvious, like the introduction, protections, evaluation, open questions. There's a bit more like in the introduction, a bit of this and that. So definition of privacy, categories of private information, threats and modeling attacks. That's actually also where a lot of the new things actually are. So I put more focus on that. Or new things which I present as new things. But let's start from definition of privacy. I like to always start by security, because that is the easier thing to define. So information security refers to making sure that only those with authorization have access. That's black and white. So it's a categorical access policy. Either you have the right to access some information, or you don't have. There's no ambiguity involved. And I have to mention that both of these definitions are my definitions. There is no community agreement on this, so that's why this is one of the questions I have in the Presemo link, which I sent, that you can comment whether you agree with this definition. But then the privacy part refers to my interpretation, and now this interpretation is also slightly different from what I have in the current version of the paper. I do want to update it perhaps a bit. So this is something I've changed this year. But so it refers to, in my mind, to making sure that the level of access to and use of information is appropriate. So that appropriate is the kind of keyword here, that it always depends on a context. And it also presupposes that the kind of the other part, so the user of the information already has some level of access, but overextends that access in some degree. One example of that would be that if you walk by your neighbor's house or apartment, and there's a window open with the curtains open, so that you can see from the street, you can see straight into the apartment to the living room. It is okay to see inside the living room because they have open curtains. It's perfectly all right to walk past the house and perhaps you see something happening inside the apartment. But if you then stop and look into the apartment, perhaps take photos, that would be a privacy violation because that kind of is unusual. They are not expecting that. So the context here defines that the usual behavior is the allowed behavior, and then unusual behavior would potentially then violate the privacy of the neighbor. So in that sense, I see this as a contextual access policy. There's always different things, and that also highlights that it's very hard to say, it's hard to define the exact rule. What is the limit? How much are we allowed to use information? Because it always depends on the particularities of the situation. Now, this definition is largely indebted to Nissenbaum's definition from 2004, but also the division to categorical and contextual is from discussions with Professor Jolly Thomas last month, or actually 2 months ago. Yes, last month it was. So I hope to update the paper with this definition. It's slightly different, slightly improved version of what is in the paper right now. I have there in the paper also a list of categories of private information, just to give a reference point. So I found it a bit hard to. So I mean, actually also, I don't remember if it is now in the paper already, but I intend to put there the reference which is at the bottom here. So Rita Singh's book, Profiling Humans from Their Voice, is a really nice book. And now I think that could be a reference that you always use when you write papers to kind of just highlight or give you like scientific evidence of how many different types of information are in speech. So like biological, so body characteristics, body size, and health, intoxication, and psychological emotions, intelligence, education, and these sort of things. Message is of course important. So the speech has a purpose. So there will be. I mean, it's communication. So it has a purpose. It tries to communicate something to someone else. So there's always a message, and that consists of then text and emphasis, intonation, and that sort of things. But also, of course, language and accent and skill level in that language. There's affiliations. So which groups the speaker kind of is connected to. And that's like the static thing. But then there's the relationship character. So the person you are kind of with whom the speaker is discussing currently. And there's lots of things like hierarchy, familiarity, attraction, and intimacy. Just an example, you would talk differently to your boss than you talk to your mother or your partner. So that kind of characteristic of a discussion is audible from the speech, or even if you hear only the one part of the speech, or potentially audible. Physical environment, that's pretty obvious. So background, distance to sensor, and that sort of things, and hardware and software. But that's just like pretty basic, which we should have clear by now, and I just hope now to have a citation where you can say that there's lots of things inside speech signals. But what was clear perhaps also before, but I tried to highlight it, make it more obvious now in this. So I made a picture out of it, is that when the speaker, there's a message that the speaker tries to convey to a legitimate recipient. So it's a private message. I call it a private message because speech. I mean, if the message would be widely known already, if everyone knows the answer or the content you are speaking, then there would be no point in speaking. So in that sense, the speech signal, so the content of it is always somehow unknown, and so in some sense private. So all speech are private messages. That's my interpretation. And now, so it's supposed to go to the legitimate recipient, but it can also go to an undecided recipient. Now, the legitimate recipient basically can almost always share the information he or she has heard. So there's quite little we can do about this avoiding for the private message to go to the undecided recipient. We'll come back to the cryptographic methods which you can do to avoid this. But if there's a message which goes to the recipient, you can't really do anything about it leaking forward unless just trusting the recipient. But what is more interesting and more productive to think about is the side information. So that's, for example, now health information or identity of the speaker that's bundled in the speech message, and we basically accept that it's going to a legitimate recipient. But when it goes to an undecided recipient, that's actually something which we can try to avoid. We can remove side information because that's not the purpose of the communication, so it's not needed. Oh yeah, and I also split. So any use of information which is not legitimate, I call it undesired use. So it doesn't have it can this leak can be from the legitimate recipient. It doesn't have to be from the channel like it's in this picture. A few words about threats. I'm not going to read all that through, but I leave it here for reference. So price gouging, for example, changing the prices when someone is vulnerable. That can happen when someone gets access to private information. They can be tracking or stalking based on private information. Someone could be extorted or humiliated publicly. They can be algorithmic stereotyping, and I think those are. Oh yeah, so there's also the harassment, inappropriate advances. Those are the most commonly referred threats. But I like to also highlight the fear of monitoring. So this is a fear. So nothing has actually happened. So if you fear that your phone is listening to you, you might put your phone away. So it can induce action. It can induce things even if nothing actually is going on. And psychological experiments have shown that the feeling of being continuously monitored can be actually very damaging psychologically. It's also a problem for democracy and free political expression. One other thing which I like to highlight from these threats is that we often, or in the media, the focus is often on the big crime type of things, or big companies doing things, or big criminals doing things towards individuals. And yes, those are where are interesting news, and the damage of that one event can be very large. But then harassment and stalking are things which are common. So that happens to lots of people, millions or hundreds of millions of people. And even if they are perhaps not newsworthy threats, but because there's so much of it, there's some evidence that they are actually, in economic terms, they are of similar magnitude as the big crime type of threats. So they deserve attention. Then moving on to attack or risk model. I think I had a question about this also in the Presema. And the thing why I think about here is the attack or risk part. So in privacy, we have very much, of course, thought about privacy attacks, and that's the right thing to do. Kind of thinking about how a potential attacker can extract private information. But I now, just a few weeks back, I realized that there are other risks involved in these systems that it might be useful to consider at the same time. In the particular case I have in one project was that there's an LLM in the pipeline, and there's a danger that the LLM does some hallucination or something like that. So there's risks involved because the LLM can do hallucinations. So in that sense, it can be good to also talk about risk models and not only attack models. But yes, but this model is pictured here is the conventional attack model, and its idea is that you have some private data. It can be anonymized, and then it becomes, in some sense, public data. So it's not perhaps public so that anyone can access it, but at least the attacker then has access to this public data. And that public data is used for the downstream application. So that is the purpose of the communication again. So it could be ESR or some service which the speaker wants to access. And now, so the attacker then can extract something from here, and it can use some found data, so whatever other supporting data it has to its use to extract private information. So basically resynthesize the private information here, which was here, which was supposed to be removed here, so it can be resynthesized here. So that's the generic usual attack model. That there's not really new here, just presenting it for completeness. But this a bit newer is from Raman's paper last year, which I think is useful to add in this context, that I think we should start to use it, attack this scenario of use in this sense, where it's really specified what the objective of the attacker and what the objective of the defense is, and the opportunities they have and any resources they have. So this is not my work, but I'm just also putting it here because I think it deserves to be more widely used. And now for this kind of is a part of the collection here. So the attack model, scenario of use, and then comes the attack surfaces, which is the part which I would spend a bit more time on because I haven't seen others do this. So this is complicated, but I'll break it down to make it a bit simpler. So there's Alice, user Alice here. So that's the person using the device. So the Alice can talk with the local device or can talk with the other people locally in the same acoustic space. And the device or the Bob can speak back to Alice, but the local device can also access remote services. For example, if Alice asks, what's the weather like in Japan? If the local device is not in Japan, it cannot know the weather there. So then it has to ask the remote service, what's the weather like in Japan? So this is the intended flow of information here. And now the red lines here, red or numbered lines, are all places where the information can leave the intended flow. So for example, if now the remote service now hears that there's a request about weather in Japan, if it shares that information with an advertiser, that will be so if that's against Alice's preferences, then that is a privacy violation. And in the same way, we can look at any kind of communication channel or any device or like other one here in the other entity in the flow chart, how the information can leak. And now look at a few examples or specific examples to make it a bit simpler. Here are now 4 examples. There's something in the chat. Let's see if it's okay. Yes. If you have questions, please write them in the chat. Or on the Presemo, which I shared. So first of all, this is now the advertiser case, which I call cloud leak, where the intended path to information is to the remote service, but it then gets shared to some other service as well. Second scenario would be where Alice is interacting with a local device. For example, let's say computer lights off. That's a command which can be done locally, but if it's then shared with a remote service, that will be a privacy leak. I won't go into details of the other ones, but you can see that quite easy to draw these pictures. And I think this would be a good addition to many papers I see to really specify clearly what is the intended scenario. And so in combination with this, in combination with this scenario of use, I would really like to see it as a picture, because that makes it much easier to understand. All right. Then we come to protections. There's 5 categories that I have identified as protections: information isolation, secure processing, privacy preserving architectures, acoustic interventions, and improving performance. I go through each of them now afterwards, but a few notes about vocabulary first. So there's also a question on the Presemo that so I used this information isolation, and now just a few weeks back, Nick Evans proposed to use data minimization, and I'm actually kind of starting to like that. So perhaps this should be used instead. So you can comment about that on the Presemo. Secure processing, that's clear. And acoustic interventions. So this intervention word comes from video privacy research, where they use video. I think it was video interventions as a term. So that I wanted to use the similar vocabulary as is their standard vocabulary. Yes, but so information isolation, so it refers to this basically an autoencoder structure, and now this is the place where which could be the data minimization. So we want to minimize the amount of private information that goes through the bottleneck. That's the purpose. And the idea is that so we would remove or replace private information while preserving the desired information. So this dashed line should contain only that information which is needed for the downstream application. And this removing information can then be done either by a information bottleneck or funnel or adversarial training. And this picture is then more related to the information bottleneck idea. So that if this is quantization, which is so crude quantization that it can only store the desired information, then that's like information theoretically valid protection. Now, whether it's information bottleneck or information funnel, so some authors have defined specifically the criteria how bottleneck and funnel are different, and then information funnel is then actually in that vocabulary the correct one. But I haven't really seen anyone else use that word funnel except the authors that one paper. So I would also like to hear your comments what you think about bottleneck and funnel, which one should we use. Bottleneck is used more generally, So it's used more because it's a more general concept. So I don't know which one would be the better word. The other approach is adversarial training. I have a picture of that in a second. I have also a picture of disentanglement here coming. So yeah, okay. So this is now the bottleneck idea. We already saw this picture, but so the only new thing is that in principle this can be devised such that it provides a theoretical limit on the effectiveness of the protection. So if it's a quantization here, then we can measure the amount of information going through here, and we can put a number on how private this is. But it's not really straightforward to do that, because then you need to estimate the information rate in that bottleneck, and that's estimation is not always trivial. The other approach was the adversarial approach, where you have a thread task here, which is trying to extract information from the bottleneck. And so if this thread task fails to extract information from the bottleneck, then of course the hope is that there would not be any private information in this channel. That is good as long as we have this threat model use here. The weakness of this approach is that if we have a larger or more capable threat model here, it can potentially extract information here, even when a weaker one was unable to extract anything. So this does not give a theoretical proof of protection. But this is a very practical, very straightforward to apply approach. So it's valuable in its how easy it's to apply. And then we have the disentanglement picture here. So now it's the same with the encoder, decoder, but now we have, instead of one bottleneck, we have several bottlenecks. So this could be, for example, that we have phonetic content in one bottleneck and the intonation in the second one and the speaker identity in the third one. And then based on the application or the downstream task, we can then pick and choose which one of these are anonymized. So I see this as the kind of long-term solution. If we can do this, then we can really have all the tools to protect my privacy. Whether we can do it is, of course, then another question. Or how effectively can we do this? The next category was the secure processing. I have only one picture of that. So the idea is that there will be a local device which does encryption on the raw data and sends that encrypted data to the remote service. And now if you use some fancy encryption methods like homomorphic encryption, then the remote service can do operations on this encrypted data and send the response back to the local device. So the remote service never sees the clear text, but only the local device can see that. So this is actually a secure, a security solution and not so much a privacy solution, because then there is actually no way of the remote service getting access to any private information. The main drawback of this is that both the computations, so both locally and remotely, are much higher than the unencrypted sending, and also the transmission is like so both are like 1,000 times larger than non-encrypted communication. So that's really not feasible currently for real world applications. So only for the most secure applications will be use encryption. Of course, the communication should always be encrypted, but this is now just refers to the encryption which can be then used for processing at the remote service. Then we have the architectures. So how the flow of information is managed such that it preserves privacy. This is the same picture as we had before. So if we reduce information from the communication to the remote device, then of course also secondary service cannot access that information because it doesn't exist at the remote service here. Local processing is of course better because then no information is leaked outside. But whether a local device can do the services you want to do, that's the main question. We can also do distributed learning type of things, where kind of local devices or edge devices then do the training of models, for example, and then only send the model updates to the cloud. Now, this has multiple difficulties here. I mean, it's a beautiful kind of idea in the sense that it really improves privacy by large margin because no raw data is going. But of course, it's not the perfect protection because also the model updates can contain private information. But then also the model updates are dependent on the model structure. So if you update your model, then you basically lose all the training you had, and there's no stored data. So this cannot be recreated. But that also means that it's very hard to compare different model structures because this training can take a long time. So there's like big penalty of changing model structure. And then there's the yes, also the overall complexity and transmission costs are here much higher than the cloud processing. Acoustic intervention is next category. So that's where, for example, now if a local device wants to talk, so wants to give an acoustic message to Alice, but if there's eavesdropper in the same room, then Eve would also hear the private message from the local device to the user. But there are two different types of things we can do here. First of all, we can use interference between audio. So if they are coherent at the Alice, but two loudspeakers are incoherent at Eve, then Eve will not hear what is being said, while Alice can hear what is being said. But Eve can still hear that something is being said. But there's also a different approach of using ultrasound and non-linear effects of kind of interfering ultrasound signals to create an audio here for Alice with two ultrasound loudspeakers. And then there would not actually be any sound for Eve. So Eve cannot even hear that there's sound happening for Alice. The cost is that then you need to have ultrasound loudspeakers, and those are not standard hardware, whereas the normal audio loudspeakers are available for everyone, or most of the people have them. Improving performance was the last category, and that's something I haven't really heard anyone else talk about. But so that addresses a threat, for example, false positives for a local device, like false positives for wake word spotting at the local device. So if you have something like a Alexa, you would always say Alexa at the start, but sometimes that activates the device. But sometimes it will do a false positive, so incorrectly identify Alexa as a starting word and then start to send information even if Alice hasn't started it. So that's a privacy problem, and the obvious solution for that is to improve the wake word spotting. So improving the performance of the wake word spotter then also improves privacy. And that happens now sometimes so usually privacy and utility are opponents, but in this type of scenarios, they are going the same direction. So I think that's important to acknowledge that privacy and utility are not always opponents. And it requires a bit thinking when it's opponents or not. Evaluation, now I see my time is already running, I have to speed up a bit. So these are pretty well known, so that there's always the privacy and utility, so how well it protects and how well you can use the downstream application. What is usually done is the objective performance metrics, so we actually computer or numerically estimate some indicators of performance. So how much information is leaked and how well does it perform in the intended task. But the subjective part is that's not something that everyone typically does. I think more people should do it. So should measure how does it feel. So both kind of how much information can you hear in the audio signal which is leaked, but also as a user interface test. Does it feel like information is leaking right now? For example, in this webinar, do you feel that someone could be eavesdropping here? It's a question we can study. And then utility is also, of course, a user experience. So does this service now do what it's supposed to do from the perspective of the user? But these are all user-centric performance measures. One aspect which I would like to highlight is that the user-centric is not all. It's an important part. It's probably the core of privacy. But there are also community and society level effects, which I think would deserve more attention. For example, if you have a smart TV at home, multiple persons can use it, and then if there is a voice command history in the smart TV, then kind of your roommate or partner or guest could access the voice history of what you have done to the smart TV at home. So that's a kind of community level effect of a smart TV, which I think should be analyzed more. Then the objective measures of privacy. Well, there's the empirical. I like to split this into empirical and theoretical. That's also something which is not really trivial. So there's some contention on whether there actually is a difference between them. And anyway, many of them are a bit on both. But so at least equal error rate is something which is empirical. So you have an attacker and you evaluate how often you have false positives and how often you have false negatives. And when they are equal, then that gives you the equal error rate. And most of these here are then derivatives in some sense of the equal error rate. On the theoretical side, there's more like I've kind of taken this more from the differential privacy type of work. And then I think the best way, so really the best way, objectively best measure of privacy is bits. So information content. How much information is there leaked? And then these log likelihood ratios and k-anonymity are related to that. But so when you talk about bits, that gives multiple advantages. For example, if you have two parallel leaks, you can sum up the bits which you get from them, and you have a total kind of leak size. But if you have two different kind of channels where you are analyzing equal error rate, it doesn't really help you to identify how much now is leaking information, how exposed you are. So bits are much easier to work with than equal error rate from a theoretical perspective. Subjective privacy. So that's then the kind of thing that when you, even if you have a phone, or let's say a phone or some service, which would be perfectly private, still some people will be paranoid, and some people don't care. So to get kind of like more people to use a service, it should be designed such that the perception correlates with reality. So if it really is private, the user interface should communicate to the user to give the feeling to the user that this is private. We can, of course, there's something like Facebook, which overpromises, so it has the appearance of being private, but actually uses the customer information, and that's then a dark design pattern, and that's unethical. So we really should aim to communicate the true level of privacy. And in my trust research, which we have done, really suggests that trust in a service is better when you communicate the true level of performance. So if you overpromise, that actually kind of works against you. So people trust less if it sounds too good to be true. And then you need lots of questionnaires and co-design methods to actually do that, these subjective measures. Legal landscape, shortly. So of course we have GDPR in Europe and CCPA in California. They are already about 10 years old now, and they have been very good steps forward. But strangely enough, even if it's 10 years already, there are still practical implementation things which are not really settled. For example, consent. It's a moving thing. What is an acceptable way to give consent in a speech system? But so I have a big criticism against those. So I like the laws, but they have big weaknesses as well. So they are based on categorical concepts. So they talk about identifiable individuals or not identifiable individuals, whereas science is based on statistical evidence, so likelihood. So how likely is something? And these are now not really, they cannot be easily kind of merged. But that's probably a problem with laws in general. So if you want to convict someone for murder, you don't say that it's 90% likely a murderer. You want to either say that it is murder or not a murderer, guilty or not guilty. So that's a legal domain problem. But then to open questions, so I wanted to here take a few kind of areas of research which I think would need more research. So first of all, this consent and control monitoring, especially now speech interfaces. So let's say Alexa at home. How should we give consent to it? Currently, I believe it's just that the owner or the manager of the device presses a button or kind of that I consent to using this. But then the legal responsibility is on the manager to communicate that consent to all users and everyone who potentially could come into that room where Alexa is. No one does that. So it clearly is not working as a consent way. But how should we design speech interfaces such that we can have a timely consent for everyone involved? I don't know. It requires research. The metrics part is also something which annoys me. I would like to have better, like I would have theoretically clean metrics which are practical to use. Currently, I don't know of such metrics. Let me know if there are some. Collective privacy. So like I mentioned that privacy is thought of usually as a user-centric thing Also the legal frameworks are for user-centric privacy. But now, for example, in this webinar, you have lots of people, and if you make questions, they are like, there's a joint privacy happening here. It's a collective privacy. And because speech is always a collective event, there's always a bit of this, what happens in Vegas stays in Vegas type of thing. So we really should think more about what does privacy mean for speech on like a higher abstraction level. It's perhaps a philosophical topic, but someone should do that. Disentanglement, I think it's the way to go. We want that, but how to do it? I've seen lots of papers doing like isolated things, but I would like to see some like a top-down approach, so trying to define everything. But I haven't seen that yet. And then finally, this perception and experience of, and also design of privacy, which is like between the user design communities and speech communities. So then it is not really in anyone's like domain. So that would need more attention, in my opinion. Yes, I made it in less than 1 hour. That's the end. Of course, this is to be continued, both in the sense that the paper is still not accepted, but also in the sense that this is a rapidly evolving community, like research area. So it's not the final word here. So now I will be happy to take any questions, and we can